Welcome to our next talk. This is Anja Kofeld, and she will be talking about lasers in space. Please give her a warm round of applause.
Yeah, hello everybody. I also would like to welcome you to my talk. As the angel already said, it's about lasers in space, and they are just more than just pew pew. So that's what I want to talk about. I'm a scientist at the Ferdinand Braun Institute in Berlin, and I'm a member of the Quantus project group. The Quantus project has its main goal to build an optical atom interferometer in space. And we started at the drop tower in Bremen, and now we're heading toward our sounding rocket, which shall be launched in the November next year. And in order to build this atom interferometer, we have to cool down atoms, and for that we need semiconductor, or we need lasers at a specific wavelength, and my job in this project is to build these laser modules. So now you know what I'm doing. My motivation for this talk today is, at first, lasers are cool. I think everybody will agree about that. I hope so. In the past years, there have been a lot of projects concerning lasers. For example, building laser cutters, building laser projectors, or pimping your laser pointer to a laser gun, burning stuff. There's some pictures I found on the web. And then there's the space side. This whole space stuff, it got more and more affordable in the previous years. There are more and more private activity in the space sector. For example, private companies building launching systems, but there are also a lot of student and university programs to build their own satellite to make science in space, science in microgravity. And I think when we just follow this development, there also will be more, there also will be some hacking in space possible in the next years, I guess. There's also a personal motivation. Whenever I tell somebody that I'm building lasers for space applications, there's always this, oh, you're building orbital death lasers. No, I don't. Actually, I'm very happy that I don't do that. And this talk will be about other applications of lasers in space. When you Google lasers and space, you find a lot of pictures like that. They're beautiful, they really are. You have your lasers, you have space, but I won't talk about that because these lasers are on Earth. These are guiding stars very often, or laser shows, both applications. Very useful, very nice pictures, here they are. Okay? Nice. So I would like to talk about a little laser 101, telling what is a laser, what can you do with a laser, what is space, and, well, as I said already, the applications of it. Lasers. Laser, light amplification by stimulated emission of radiation. Yeah, okay, we knew that. It's a device emitting monochromatic and coherent light, and that's nothing else but light with the same wavelength, in the same direction, in the same polarization. With that properties, you can focus photons on a very, very small area, because there are a lot of photons doing the same thing. And that's why you have a very high power density, and that's why you can use lasers, for example, for welding, for cutting, for delivering data over a very, very long distance. What do you need to build a laser? You need an active medium. This active medium, or the electrons in this active medium, they are stimulated by a pump. This is either an optical pump or an electrical pump or whatever pump. And you need a resonator to sort out the right photons. And when it comes to the classification of lasers, you basically vary the active medium. So, for example, there are solid-state lasers where you use a crystal. A very good example for a solid-state laser is the neon-doped yttrium aluminum granate laser, the YAG laser, as we used to call that. This laser, or this type of laser, is used in the industry, for example, but you also find that in laser light shows. And yeah, there are a lot of applications for that. In contrast, there is a semiconductor lasers. They are a lot smaller. You see like the green one on the left-hand side is the arc laser. In the center, you find the semiconductor laser. They're a lot smaller. They're cheaper. They're more efficient, and you can tune the wavelength over a certain range. As an example here, there's, for example, there's the indium gallium nitride laser, which you will find in your Blu-ray player, or the aluminum gallium arsenide diode, which is commonly used in DVD players, stuff like that. I think everybody owns at least one of them. There are gas lasers, for example, helium neon lasers. The helium neon laser was the first laser built in the current wave mode, and it's now used for example, calibration or in schools. And the CO2 laser is one with a very, very high power density. It's a pulse laser used, for example, for welding. And then there are the dye lasers, which can tune the wavelength on a very, very long range. They are very often used for spectroscopy, for example. So whatever you want to do, you have to choose your laser or your laser type with your application. And they vary a lot in their output power, in their mode, whether they are pulsed or not pulsed, in their wavelength, but also in their size and complexity. Yeah, and you just have to choose the right one. And this is important, especially when we are going to space. Here are some common applications for lasers. You use them in measuring, in optical data transmission. They're used in the multimedia sector and also in the production sector, you call it, but not only at home or in industrial or in medicine, but also in space. So space, here we are. The common definition of space is 100 kilometers above the sea level. But whenever there's, for example, an Apollo astronaut, when they're talking about space, they're talking about 50 miles, which is an older definition of space, based in the US. You can go to space via satellite. You have the space station. Very often, or sometimes at the space station, you have an operator, like a person operating your experiment. Might be useful. There had been orbiter experiments. Sorry, especially in the times with the space shuttle. And there are sounding rockets, which are rockets going up to approximately 1,000 kilometers max and falling down, but in the meantime you can perform experiments in zero gravity. Why do you want to go to space? Well, there are a lot of reasons. For example, the observation of distant galaxies, of the Earth's weather. There are communication satellites just to transfer data. You want to perform science up there, for example, because of the lack of gravity or the lack of atmosphere. There navigation, and there's also the military purpose. So can't deny that. But it's not that easy going to space. Whenever you want to go there are a lot of restrictions. For example, the size and the weight. When you want to launch something into space, you have costs approximately $4,000 to $5,000 a kilo. Although this price is decreasing, but it's still high enough. You're very limited in your power consumption because you don't have everything, it's a closed system, right? You have your solar panels, but that's it. And sometimes some other energy sources which may disappear after a while. Everything you want to send up there has to survive the launch, and sometimes it has to survive the landing when it's falling or when it's coming back to Earth. There are applications where you might use that. Very often there's no operator, like no one pressing buttons. So everything has to run autonomously, and your stuff needs a quite long lifetime because you don't want to switch some parts once a year on a satellite. So you normally don't do that. So, as I said in the beginning, I'm a scientist, and this is a lab. It's not my lab. I'm very happy about that. But this is an experiment quite close to that what we want to do. And as you might assume, this is not a good idea to launch that. It won't hold. It won't survive the launch, and probably it won't work up there. So what did we do? Well, you have to choose an appropriate technology. That's why we are using semiconductors, for example. They are much smaller, they are much more energy efficient. You have to space qualify all the components you're using. You have to take care about the materials you're using. You can't use whatever adhesive, for example, because you have this outgassing problem. Your device has to operate in vacuum, very often at least. You want to minimize everything, and you want to fix every part. You don't want to have that much movable parts, because there won't be anybody to fix your setup afterwards. And you have to work in a clean environment. When you integrate something, dust is a problem, for example. You don't want to have any particles around. You have to test and characterize everything, and once again, again. And you have to document everything, like more than everything. So these are some pictures of my lab. On this side, you see a characterization setup. In our lab, it's not a clean room yet, because we are not working on a satellite mission. It's just a sounding rocket. But we wear these funny lab coats and these funny hats. So maybe you see that person there in the middle is a colleague of mine. If you see that, hello. And on the other side, it's the integration station of our lasers, and some setup around to characterize everything. So just to show the result of our effort, it's a semiconductor based master oscillator power amplifier. On a size like that. It's like 8 centimeters long and 2.5 centimeters wide. It has no movable parts, and it hits a specific wavelength, because we need that for our application. We want to cool down rubidium. And it has an output power greater than 1.2 watts. So how much is that? Well, a laser pointer has 1 milliwatt. An illegal laser pointer has 100 milliwatt, and this is 10 times stronger. And the efficiency we have now is 22%. When we fuck off the wavelength, when we don't care about that at all, then we can achieve even higher efficiency and a higher output power. But in our application, the wavelength is mandatory. So now, when it comes to testing, you need some documents telling you what to test and how to test, and so on. So there are a couple of standards, and most of the standards are based in the military sector. The standard which is very important for us is, for example, the MIL standard 883, which describes test methods of microcircuits. And that's a really huge document. It's about 640 pages thick, and it describes the purpose of a test, the apparatus, the test conditions, and the procedure and the failure criteria of environmental tests, of mechanical tests, and of electrical tests. So in this picture down there, you see our laser system. The silver tube is the entire laser system we have in our experiments. It contains 8 lasers and a spectroscopy module and a switching module. And this setup is on a shaker. So here we are performing the random vibration test on acceptance level, and we passed. So I'm also very, very happy about that. And of course, there are a lot of more tests we have to perform, but it looks good, so wide. So now we have our hardware. What else can we do with that than building weapons and atom interferometers? Of course, we have the interferometry is a very, very common application. Just to name the LIDAR system, it's a combination of radar but with light. And this one is used for as altimeter, for example, or to map surfaces, for example, of distant planets, of the moon, of the Earth, whatever. Systems are used. They are working well. They're sending out a beam and they're analyzing the reflected beam concerning the phase shift, and then they know how far the reflector is gone, how far it is away, and yeah, with that you can measure very precisely the distance, and it's you need that, for example, in docking operations. In the picture up there, you see the ATV. The ATV satellite docking to the space station. I think it was in 2007. You have several other satellites, for example, mapping the planet. And there's also another mission I would like to point out. This is the LISA mission, which wants to measure gravitational waves. Unfortunately, the LISA project got cut down, and now it's just LISA Pathfinder, a proof of concept mission which is scheduled in 2015. But there are, of course, a lot of more applications. I just picked out some, which I find interesting. Spectroscopy is also a very, very nice application. When it comes to spectroscopy, you analyze the beam concerning of the absorption or relaxing photons coming back. So you're also sending away a laser beam, and it comes back, and you simply look what is coming back, and with that you can analyze matter or the chemical composition of matter around. For example, on Curiosity, the Mars rover, they're looking for methane gases by spectroscopy, so they have at least 2 spectrometers on board of this little guy. And another application which gains more and more importance in space are optical atomic clocks. It's a timekeeping device, but optical clocks operating with lasers are even more precise than the radio frequency operated ones. And there are some new generations of optical atomic clocks also heading to space because they're even more precise in space. For example, there's the ACE mission. It's a French mission which was scheduled at the end of this year. Unfortunately, I didn't find a newer launching date, but I think it won't be launched next year. But somebody, maybe you know even more than I do. And there's also another mission called STEQuest, which is still in preparation. So this is everything I have on measurement. Free space optical communication is maybe an application most of you know what it is. You have your optical carrier, the laser beam, and you modulate your data either with phase shift keying or with binary on-off keying. The binary on-off keying is the most common one, and compared to the commonly used RF transmission, you can go over longer distance. It needs less power, and you have a higher transmission rate. But still, it depends on the atmosphere and the weather on Earth when you want to transfer data down to Earth. As an example, I can name the laser communication terminal. It's built from TSAT, and it was first tested on the satellite Artemis, and it had a downlink and an inter-satellite bandwidth of 50 megabits per second. This was in 2001. In 2008, there was another inter-satellite connection between TerraStar X and the Enfire satellite, and they received 5.5 gigabits per second. The There's also another US mission currently ongoing. That we have it's called the Lunar Laser Communication Demonstrator Mission on the Lunar Atmosphere and Dust Environment Explorer. This was launched in September this year, and in October they received a downlink of 622 megabits per second. So this is state of the art right now. So that's everything I have. I still think lasers are cool. and I hope you agree with me that there are a lot of applications for lasers in space, and I also think that reaching space is challenging, but it's not impossible. So it's pretty doable actually. There are some initiatives for non-professionals or for I'm not sure how to call that for everybody. For example, the amateur radio satellite organizations, they are worldwide. There are, for example, the Rexus-Bexus experiments. These are sounding rocket and balloon experiments for students. There are, for example, the CubeSat projects, which are, they designed satellites of the size of 1 liter, like that size. And they can go as piggyback payload, for example, on commercial satellites. So this is an opportunity to get to space pretty cheap. I also want to name the Google Lunar X Prize with the part-time scientists as the last German team, I think. They want to build a lunar rover, and there are also a lot of other initiatives and projects which you can find. Yeah, thank you.
Thank you very much, Anja. Thank you very much. Now, if you have questions, could you please line up at the microphones here so we can record it. Our signal angel, do we have questions from the internet? No, not right now. Okay, then let's start with microphone 1.
There's basically one thing. The French device is going to be launched in 2016.
Okay.
And another thing, why do you? It's a double question actually. First of all, why do you go in microgravity with atom interferometry? What do you promise yourself from that?
The plan is to redo or to find the answer of the question whether the Einstein's equivalence principle is still correct. So the main goal is to go up with 2 species up there, measuring the gravitation, and compare that. And we need to go to space because it's more precisely measuring up there.
Okay.
You have a longer measuring time.
And another thing, I happen to know some friends of mine who work scientifically with lasers, and the alignment ends up to be the pain in the ass of everybody working on that field, professor touching random stuff, and the experiment is ruined. How exactly do you harden a setup for launch? I mean, you have the G-loads, you have vibrations, you have random stuff happening, so how do you do that? I mean, it's a quite sensitive setup, if I'm not wrong.
It's a very sensitive setup, that's true. But when you plan it, when you know that it has to work autonomously from the beginning on, you can design it to make it independent of professors running around touching things, for example.
That's not the thing. How do you cope with misalignment, for example? I mean, you will have some mirrors or some beam splitters or whatever, and if they get moved, that's it.
We use very, very small components, like very, very small lenses, and we glue them. We fix them on a bench, so you can't align them anymore. When we are building or when we are integrating our stuff, then we are aligning that actively, so the laser is on switched on, and then we align the components that the output is what we expect it to be.
Okay, let's have a question from the other microphone over here.
First of all, thanks a lot for this great overview talk. I just have a very quick remark about the LISA mission. I'm very happy to announce that just recently we got fully funded by the European Space Agency, and in 2034 we will fly with $1.2 billion budget. Yes.
Sounds good.
Which mission? Which mission? LISA.
The LISA mission,
Oh, fine.
hunting gravitational waves.
Congratulations. Go ahead, please.
Hello? Oh, okay. My question is about how do you, when you shoot something up and make an experiment, you probably won't shoot one satellite for only your project. So are you working together with other departments, and then you, like, everyone gets 1 square meter for his experiments, and then you shoot them up, and all experiments run independently on one satellite?
It depends on what you're doing.
Okay.
In our experiment, we have one rocket just for our experiment, but it's not just the Ferdinand Braun Institute building that stuff. It's a cooperation of a lot of institutions and universities. Mm-hmm. And when it comes to these satellites, experimental satellites, they very often go as piggyback payload. That means you have a commercial satellite, for example, a communication satellite, which is launched anyway, and they're normally much smaller, so they're sitting just on the side and wait for the launch.
When you're talking about piggyback payloads, don't you have some problems with the whole space trash problem? That's because you can't just say people can go and shoot stuff up there if there's one space trash problem anyway.
I'm not sure I got the question.
You say, for example, I could just build something and shoot it up as a piggyback payload.
Well, it's unfortunately not that easy, of course.
Okay.
But it's not impossible. Like some years ago or some decades ago, it wasn't possible for a private person to even think about building your own satellite.
Okay.
So, but you need some funding. You need a group basically, and maybe you're lucky and you get to your goal at the end.
So I can't just, if I get it to build a rocket myself and shoot it up, is it allowed? It just from the law?
I don't think so.
Okay.
Okay.
I have one question.
Go ahead.
You mentioned the mission concerning analyzing the moon dust and this moon mission, but you didn't mention who are the partners. Is this a project by ESA? Is it a project by a cooperation of several agencies, or the private?
It's a NASA project.
Pardon?
NASA, the US.
Also a NASA project, thank you.
Yeah.
And then another question, since a lot of the clicks have come down by gigahertz, and those missions, those frequencies are also reserved for astronomers. Do you have some feedback from the astronomer community, how they are they concerned that their frequency will be less and less, more laser communication we will get, or other optical communication or other laser applications? What's the standing point of the astronomy community, because they are using also the high frequencies in the gigahertz, 5.5 gigahertz.
I have no feedback on that.
Okay, any more questions from the internet? How about our signal angel? No questions from the internet. Okay, then Anja, once again, thank you very much.